So, we are discussing about the different packaging, right. So, for food materials, after it is being produced, before it is sold, it is being packed. So, in this dairy and food products, food process and products technology, in lecture number 59, we now come to the packaging which is recently coming up as modified atmosphere packaging, or that can be told in short as MAP or MAP, right. So, this modified atmosphere packaging, right, is not very age old. Though the technique has come up very recently, but I cannot claim that it was not also available earlier. The same thing was available, but it was not nurtured. So, nowadays it is being nurtured and being looked into in that way, right. So, as we said, what is the genesis of this? As we said that when you are doing vacuum packaging or flushing with nitrogen, that time you are removing oxygen, right. Why you are removing? Because oxygen is primarily it is helping the anaerobic organisms, as well it is doing the oxidative changes. So, this is not desirable, right. Now, you just think this way that of course, I am against using plastic because that is spoiling the really this is spoiling the entire environment, and some alternative should come up. Someday I believe it will come up. Okay. But because necessity is the mother of invention. So, for that someday when all over the world people will be very much like people now are cautious about this ozone sphere, right, and this way someday and global warming, these kind of sensational things when it will come to the world, plastic also will be left aside. Some alternative has to come. But yes, as of today, plastic is a part and parcel of our daily life. We just cannot avoid it at the moment. So, in that case, say you have taken one guava, right, or now it is the mango time, this is the mango time in India. So, you have one mango and you have wrapped that mango with one polymeric film, right. So, that polymeric film, of course, many things are to be said, but from the bird's eye view, what we can say that since you have wrapped with the polymeric film, so that is making a barrier between the mango and the outside atmosphere. Outside atmosphere, what you have? Air. What it has? 21% oxygen and 79% nitrogen. Whereas inside, what did you do? You have put a wrapper, and this mango being a product which respires, right? Because you have seen that mango, when it is in the unripened form, it is green, and when it is in the ripened form, it is yellow, right. So, this stage of ripening is happening because of is taking respiration, it is doing respiration, and that is leading it to ripening, right. So, what you do in control atmosphere storage, you extend, let me just give a, so what you do, this you make a plot right? This is oxygen uptake and this is time, right? So, the moment you have plucked from the tree your, say, the mango which we are talking about, it had a respiration rate here, right, and it was absolutely green in color, right. So, it is not ripened on the tree. You have you have plucked it so that you can keep it for a longer period, right. Now, from here, when you plucked it, what it does, because in the new environment, this fruit that takes some time, the same as our all mammalians or our child are coming into the earth when they are taking birth from the mother womb, this is cut, right, that umbilical cord is cut, that means detached from the mother. Earlier everything was being supported by the mother, now it has to be on its own, the baby. Same is with the mango. When it was in the tree, everything was supplied by the mother tree. But when this you have plucked out and you started from here, right? So, it takes some time to acclimatize, right? That is why the respiration rate comes down. And then when it acclimatizes, right, this how long you cannot quantify unless you do experiment, right. You cannot quantify unless you do experiment. That is why it is a tentative or one representative line, right. So, it is then going up and then reaches a maximum and then it starts declining, right. So, this called senescence, coming to the senescence and the entire ripening that takes. This is the process where your ripening is taking place, right. This is the process where your ripening is taking place, right. And from green, this was green, now it has become yellow and also eatable, that soft also, right. It has become soft, yellow and you can eat. So, now what it is, assume that you have tied this end to one and you have tied this end to another and now you stretch it, right. Now you stretch it. So, if you stretch it, then it can be said that this curve, if you can make like this, right, then the number of days by which it was getting ripened, this is number of, say, days by which it was getting ripened, now you have made it to that. So, you have extended the life. If it was for, say, 5 days, now if you can make it, say, 50 days, right. So, 5 days you have made it to 50 days, this is time and this is that rate of oxygen uptake, right. So, if you do this, then that is what you are doing in the controlled or modified atmosphere. So, in modified atmosphere, what you are referring to, I cannot draw the mango in better way. Say this is the mango and you have put one wrapper, right. You have put one wrapper. So, ambient, this ambient is with air which contains 21% oxygen and 79% nitrogen, right. Whereas this inside it has little oxygen definitely, because the quantity or volume of the air inside is very negligible, right. So, that will not allow the oxidative changes in the mango as well the ripening or growth of the organisms or the ripening of the mango. So, what will happen? This mango will respire how? This whatever oxygen was there, you just imagine another similar case, that on this on sea level you have plenty of air and oxygen. So, you are breathing as and when as much you can, right. Now, just imagine if you have been fine, if you have not been, then imagine that you are taken to, by some means you are taken to the highest peak, say Mount Everest, right. And in that Mount Everest oxygen level is very low. So, what, you will die? No, you will not die the moment you reach there, because there you will try to acclimatize with the changed condition and your rate of respiration will go down, right. Your breathing also will go down. So, here since oxygen is not available, so what do? Your breathing then becomes less. So, here also since oxygen is not there available, so its breathing will be reduced. So, that means you are stretching like this, right. You are trying to stretch the curve like this, right. And the moment you are doing that, then had this mango you bought it from the market today green, maybe by 3-4 days it has become yellow. But if you have kept it like this, then it may be instead of 3-4 days, it could be 10-15 days after it is becoming yellow. So, you have extended the life. So, that is the crunch of the entire modified atmosphere packaging. This is the basis, right. So, now let us look into all detail what we are saying. So, actually not so much accustomed. So, that is why now let us look into actually how modified atmosphere packaging is being done, right. So, modified atmosphere packaging or MAP, the genesis we have already said, normal air that contains 21% oxygen and 0.03% carbon dioxide. It was found that low oxygen, high carbon dioxide levels slow ripening and reduce the development of some peel disorders and inhibit pathogen growth. So, MAP was first recorded in 1927 as an extension of the shelf life of apples by storing them in atmospheres with reduced oxygen and increased carbon dioxide concentrations. In UK, Marks and Spencer introduced MAP meat in 1979. In 1981, bacon, fish, both fresh and cured, sliced cooked meats were introduced into the commercial market, right. So, gradually it is coming up to the market and maybe someday it will be also extended to many other products. So, what is then meant by MAP, which we have already discussed in detail? Let us see what we are trying to say here. Here we are saying that modified atmosphere packaging or MAP is a long established and continuously increasing technique for extending the shelf life or fresh food products It requires specialized machinery to flush out air from the packaging and replace it with a different gas or mixture. MAP aims to provide longer shelf life, maintain sensory attributes like color or appearance, and achieve the food safety of the product. Then gases used in MAP and their functions are like this. Carbon dioxide gas is used. It inhibits the increase of most aerobic bacteria and is the most important gas in MAP. Tentatively, the higher the carbon dioxide, the longer the durability of the perishable food. Then nitrogen, an inert gas used to expel air, especially oxygen, out of the packaging, used as a filling gas to equalize the effect of carbon dioxide absorption by the perishable. Oxygen should be excluded from MAP except some cases where it can bring positive results in food preservation, helps in keeping color, makes respiration possible. Then noble MAP gases used are like this: high oxygen MAP, argon and nitrous oxide NTO MAP. These are some of the gases which can be used instead of oxygen and extend the life. But obviously, argon is not available everywhere, but this is one technique which can be used, right. If argon could be made available everywhere, is good, but it is a scientific process where you can do it, right. High oxygen MAP inhibits particular enzymatic discoloration, prevents anaerobic fermentation. Argon and nitrous oxide by the way, you know, in school you have seen nitrous oxide, you call it to be laughing gas, no. So, these are classified as miscellaneous additives, particularly in European countries or European unions, right. Argon can more effectively inhibit enzymatic activities, microbial growth and degradative chemical reactions in some of the perishables. Argon and nitrous oxide increase the shelf life by reducing the fungal growth, right. I am moving a little fast, the reason being a lot of things are to be shown, time is very limited. A gas composition used in MAP for different agricultural product is like this. Normally, the gas is carbon dioxide, nitrogen or oxygen, right. For red meat, this is 30% carbon dioxide, 70% oxygen. For pork stick, 20% carbon dioxide, 30% nitrogen and 50% oxygen. For beef, 20% carbon dioxide, 60% oxygen. For chicken, 30% carbon dioxide and 50% nitrogen and 20% oxygen. For hard cheese, 20% carbon dioxide and 80% nitrogen, no oxygen. For fish, 40% carbon dioxide, 30% nitrogen and 30% oxygen. For trout, 50% carbon dioxide, 15% carbon dioxide, 65% nitrogen and 20% oxygen. For fresh pasta, 50% carbon dioxide and 50% nitrogen, no oxygen. For pre-baked rolls, 70% carbon dioxide and 30% nitrogen, no oxygen. For pizza, again 70% carbon dioxide and 30% nitrogen, no oxygen. For product meat rolls, 30% carbon dioxide, 70% nitrogen, no oxygen. For cooked ham, 40% carbon dioxide, 60% nitrogen, again no oxygen. For fried sausage, 30% carbon dioxide, 70% nitrogen, no oxygen. But for fruits and vegetables, generally 5% carbon dioxide, 90% nitrogen and some 5% oxygen. Generally, it is said 2 to 5 oxygen and carbon dioxide. Now, 2 to 5, that depends on what fruit, because fruit vegetable is a wide market, wide variety, right. So, ready-made salad is 30% carbon dioxide, 50% nitrogen and 20% oxygen. So, this way different gas compositions you can maintain and you can provide the extension of the life accordingly, right. Now, it comes how you will make it, right. So, compensated vacuum used for MAP is like this, that removes air from inside the package and then breaking the vacuum with the desired gas mixtures. Replacement of air being done in two stages. Speed of operation is much slower than the gas flush technique. For oxygen sensitive food materials, compensated vacuum is the best choice. Then the machineries which are involved in MAP are like that. This is the thermoforming packaging machine, then vacuum creating machine, then form film seal machine, either horizontal or vertical. So, the thermoforming machine looks like this, right. This is a schematic, of course, this is a schematic one, right. So, it is forming, right. So, thermoforming, this is going like that and then ultimately with the product it will come out, right. Then some other like vacuum packaging, here you are keeping this thing and that is connected to a vacuum, right, that is connected to a vacuum. So, it is sucking and the composition here is from there is being sucked, right. And then form fill seal machine, it can be horizontal or it can be vertical. So, vertical is this one and the horizontal is this one. So, you see it is going like that and then this part is also coming along with it and making the sealing, and this is the sealed product, right. You see how it is coming out and that sealed product is going like that. This is horizontal. Similarly, for vertical, your packets are coming like this, packets are coming like this, and then this form making, this is from their roll it is coming and making this and getting it cut here and you get the similar product like this. This is the form fill and seal machine, right, both horizontal as well as vertical, right. So, when it is coming like that, then what you need is that this fill and seal, once that is done, then the gas flush technique is another one. So, which we have already said that with the nitrogen gas you are flushing off, right. So, gas flush technique that comes in like this, that normally accomplished on a form fill seal machine. Air replacement inside a package is performed by a continuous gas by and large inert stream. Atmosphere surrounding the food product is gradually flushed off. Key factor is the speed of the machine and process being continuous, finished product obtaining rate is very high, right. Then we come to this level, that what are the then advantages of the map. The advantages of the map is like this: longer durability of perishable food or decrease of spoilage, germ growth is reduced, form and texture of the product is retained, natural color of the product is preserved, need to use preservative is greatly reduced, shelf life of the product is extended, and economics of the system that depends on the extent of expansion of the storage life of the product. The how much you are extending, that will dictate how much money is going to be involved. Some disadvantages are always there, because any advantage has to have some disadvantage. Light with dark, that is a must, right. So, it is not that it is always one way, both ways generally. Sometimes both are equal, sometimes one predominates very high and sometimes the other one predominates. So, depending on the situation. So, disadvantages are like this, that capital cost of the gas packaging machinery is high, cost of gases and packaging materials are also high, cost of analytical equipments to monitor the quantity of the recorded gas mixture or to correct the gas mixtures, that analytical equipments are also costly, cost of instruments to ensure the quality of the product, transport cost owing to increased packaging volume, because you have given a wrapper, so that is increasing the volume. So, that in turn will increase the transport cost of the material, which comes under the total cost of the material is being sold, right. Then increased retail display space owing to increased package volume, potential danger due to growth of foodborne pathogens owing to abuse in temperature by retailers as well as consumers. So, this I have been saying that this is the apprehension of all the scientists, all the people, that abuse of the process. That abuse, I gave the example of these our normal malls and others, where frozen materials are kept in the freezer, but the top is open, right. So, this is simply abuse of the system, that is not desirable. Here also like that. Benefits of map is lost once the package is open or gets leaked, because you have put one wrapper as we have shown. So, in that wrapper, once it gets leaked, then the external ambience that goes in. So, your entire effort, entire packaging, entire cost, that goes out. So, you have to be careful that there is no piercing of the packaging material, right. So, hopefully with this high oxygen map, with this we come to the end of this class, and we say that packaging can be of different now packaging industry has come up to the market into the way that more than the product, packaging is dominating rather. So I don't feel personally as scientist that should be, but packaging definitely improves the life. So the way packaging is getting developed, the way new and new packaging techniques are coming in, hopefully someday that will replace the use of the plastics or polymers. Okay, so thank you.